Is this color fine? So I would be writing, not moving and then giving you, because I would be writing and red is better. Okay. Is red is also better, na? Okay. So, okay. What is encoder? Already I have said, representing in a different form. Transform the input. Transform / represent in a different form. That's what is your encoder. When what are the initial available concepts in this is I think what I recollect is DPCM. All variants of pulse code modulation, all variants of digital modulation methods are some or the other form of the encoding methods, and later came into a channel encoding methods. So initially they are used to reduce the redundancy present in the data. All digital encoding methods, when people started digitizing all the signals, when you digitize all the signals, what you get is, you get a series of, say, when I digitize my voice as an amplitude variation. So every second I say 20 samples or 40 samples or whatever the number of samples. When I sample that data, I have a particular voice intensity every sample. How do I transmit, or how do I say that? And whatever the number I get, 25, 35, 40, 20, 10, 0, 0, I get series of numbers and I say them and then transmit. But there is a lot of redundancy present in doing that. How do I reduce that redundancy? Instead of sending actual data, you take a difference between the previous sample and the next sample. Only first sample is sent full, next sample only start transmitting only the difference. That was a very cool way, or very naive way of reducing the number of bits. And on similar concepts, there are large number of concepts and variations have come over the last 60, 70 or almost nearly 80 plus years. Lots of variations in the digital coding methodology for audio, video, image, and all of you know what methods are JPEG, variation of JPEG, and for MPEG 4, or also 364 are the different methodologies of this encoding, where the goal is to represent the data as remove redundancy as high as possible. So represent the data as compressed, or by taking as minimal requirement as possible. Those are the philosophies. But when you come to in the deep learning or in the so-called machine learning framework, what is the initially it did start with the what is called a simple encoder for the reconstructing these images back. But however, when you have the first auto
disconnect.
Oh, I'll move on to disconnect. Okay. So when you start with auto encoder, Autoencoder meaning you are learning the encoding methods from the data itself. So typically which is suitable for unsupervised. Why people started calling it as a autoencoder? Because of its connect with the unsupervised. You are not tagging the data to learn the features. So the so-called the vanilla autoencoder, what you have an input X. This is the typical representation of an encoder. Nowadays people, this is exactly borrowed from the compression that encoders were doing. You have a larger dimension and the dimension will get reduced to small. These days people also use simple square box for the encoder, but this is a typical encoder symbol most of the methods use. What you get some different variable z, which we call as a latent space. Z is given to, this is encoder, given to a decoder, and what you get back is X cap. So what is the optimization concept that you are using? You are minimizing the loss between X and X cap. So we'll use a squared loss itself. People do different losses, but we'll assume the SSD loss we are minimizing, which is most of the vanilla encoder tries to do. So what is that we are saying? What does this mean? When I say the latent space Z is some E phi of X, and X cap is d theta of Z, isn't it? What are phi and theta? Are the parameters of encoder and decoder. Parameters, weights, W's of encoder and decoder. What do I, if I replace or if I put a Z value, so what do you get? Isn't it? So what you are trying to do, you are trying to minimize the difference between X and X cap. Minimization over what? What are you optimizing it? What are the parameters? What are the parameters? Parameters are phi and you minimize the X difference between X and X cap for the parameters phi and theta. That's what is the, see, minimization means on what parameter you are minimizing. You are minimizing the error, but for what? It's a regression, whatever. You are minimizing the error, whatever the measured and the predicted value of y for all. On weights wi or theta, whatever your notation you have been using. Either you are using as a weight wj or you are using as a theta. Which one you are comfortable? Theta or w's? Are you using w's? What does this looks like? What does E phi of x looks like? What does E phi of x looks like? It's exactly, it is what is y h of x looks like over theta. Your hypothesis, isn't it? It's exactly the similar. It won't be very different. But your whatever the optimization, so prediction you are doing, you are doing something different. That remain the what are the dependencies of this? Is a function of what all parameters? See, in whatever you have done for your simple neural network, that all that remains exactly same for this as well. It won't be very different. It won't be different at all. Not very different. It won't be different at all. What is your encoder? What is your autoencoder which transforms x to z? Is a set of neural layers, some input layer and the output layer and some hidden layer. How do I represent that? How do I represent that? How do I represent my neural network? When I say I am giving you the model, I am taking the model, I am learning the model, means what? Your parameters. How do I represent those parameters? W transpose x plus plus some constant. So what is this function? It's a weights plus input and some biases. Usually you write G of W transpose X plus beta. Notation can be different. People call theta transpose X plus B or W transpose X. Here it will be phi transpose X plus B. Here this would be G of phi transpose X plus phi transpose X plus B. What are phi's? Phi's are your weights. So when you are learning this, what are the main things? How does this looks like? When I represent this way, how does this looks like? So the input dimension is some this. What I have set of interconnects. I'm just showing you some random connect, and output are, say I'll write a final decoder output. This is encoder, this is decoder. You have is it fine? You have typically the dimension k is much smaller than here. K is, at least it has to be smaller than that used to be when we were doing the compression. But when we have Okay. So you want me to stand here and then talk? Okay. Restricting my movement also restrict some thoughts in the mind. So I'll try to stand here and then do it. So what is this Z is latent representation. If I do this and just solve or just do x minus x cap square, minimize over phi and theta, what are the challenges or problems? You know, simple 3-layer or 5-layer your encoder decoder you do and back propagate the loss, and you know what to expect. And if I do directly this, what are the challenges? First is, how do I do it? Before arriving at challenges, how do I do it? How do we do it? I had written for the whole auto regression model. Just I'll check what all to skip and then give you only few things which are essential. If you compare with PCA is also doing kind of a dimensionality reduction. If you say the autoencoder, what are the AEs are doing PCA and autoencoder? What are the AE and difference between PCA and AE? All of you know PCA. I think last class I did talk about PCA. PCA is principal component analysis, which again the encoding happens based on the data. Your bases are derived based on the data itself in PCA. What is the difference between AE and PCA? What is the difference between AE and PCA? So if I have a, say this is a kind of a data distribution, if I have, the PCA selects, this is PCA, this is selects as a basis. What the autoencoder does? It understands the entire set of these things, set of bases, as a manifold. What is a manifold? Manifold keeps the set of vectors which are continuous to represent the data. So the autoencoder, with whatever the latent space representation features, you are learning the manifold of distribution of the data. That is a major difference. You are learning the manifold representation of the data. That means you are remembering the data. You are memorizing the data. But if I memorize the data exactly, what are the challenges? If I memorize exactly, what's your name? Vaishnavi. Vaishnavi height is 5 and her weight is exactly this, and she wears specs and always wears a black t-shirt or the black dress, and Vaishnavi comes suddenly in a new avatar, will I able to recognize Vaishnavi? What is the fault? The way I have memorized Vaishnavi. Am I memorizing the features so that I am able to recognize Vaishnavi in all the appearances of Vaishnavi? What is the goal here? What is the goal of encoder? Which is a major block of any unsupervised learning, is I want to memorize the characteristics of the data, and at the same time I don't want to memorize them so that when the new data comes in with a similar things, I'll not be able to deviate and say that this is exactly belongs to this class. Are you getting what is that we need to do? If I exactly do this, what I am doing, I am memorizing the data. As a autoencoder, as a concept and principle, what I need to do? I need to unlearn that whatever I have memorized, or I need to have a room for the data to be sensitive enough to its characteristics. What I want to learn? I want to learn data need to learn and sensitive to the characteristics of data, and I need to learn, and it needs to insensitive to it needs to learn, or it also need to learn whatever the variations available in the appearance of that data. For example, if I say 0, there are how many varieties of writing 0? I need to learn the characteristics of 0, but at the same time that also should learn or accommodate all the variations that are present in the 0. So how do we do it? What is the key to do it, and how do we do it? Are you with me? So how do we do it? How do we do it? We have been doing in most of your machine learning classes as well, in the learning base. How do you do it? How do we do it? Typically when we say do the regularization in the supervised way, what we have done? We have added a term. In the typical term we have added, what is that we have added? Summation lambda j of wj's for all j, isn't it? This term we have added to the previous term. Yes or no? What is that we are doing there? We are making some weights to go to 0. Isn't it? What does this by adding this term, what are we making? We are making weights of the model to go to unlearn those weights, or make those weights is equal to 0. Make those weights equal to. So instead of making the weights equal to 0, if you make activation functions to 0, this leads to a type of autoencoder called any name? Yes. Sparse autoencoder. Here you are not making weights equal to 0, you are making activation functions to be 0. Why? Sorry, again I am coming back. Why are we doing this? For this. What we want to do? We want to accommodate variations present in the data. We don't want to memorize actual data. I am seeing 20 data points. I cannot visualize all the variations if I exactly know. It's as good as an exact fit, overfit. If I do the overfit, any outlier, any small variation comes, will I be able to judge that correctly it belongs to that? You will not be able to do that. If I don't want to do the exact fit. I don't want to do the any overfitting. Overfitting a data gives you 100% accuracy on that data. When the new data comes in, your accuracy goes havoc. We don't want our models to behave in that way. What we want a sane variations of the data to be taken care while developing our model. So here in the sparse autoencoder, what you are doing is just type what are the characteristics of sparse autoencoder. In Google Chat or Meta AI, in WhatsApp, whatever, you type. See, I am making you to learn and understand things and meaning of what the text is being written. That's more important when you want to apply. Nowadays, all the information you will get on the either in ChatGPT, but whether ChatGPT is giving you right answer, what does that mean when it says that if I want to implement that, how does it looks like, that you need to understand. So what are the characteristics of sparse autoencoder or sparse AE it is giving? See, how does the loss function looks like in the sparse AE? How does the loss function looks like in sparse AE? One is this remains the same. Plus there has to be something, isn't it? Regularizer, the way we have added for weights like this. I have added plus here. How does this term looks like? How does that term looks like? Anything? You have to think. See, writing that and then giving you answer doesn't take much time. But at the end of the day, that what you are learning to memorize what I am saying. But at the end of the day, do you want to do that? Do you want to do that? Obviously no, isn't it? If you don't want to do that, then you need to understand why are we arriving at that and how we are arriving at that. Then you can apply to many different problems, and then you can be very, very successful in whatever your thoughts. How do we arrive at that? What are the characteristics of autoencoder and the sparse autoencoder? Characteristics of autoencoder is called vanilla encoder. Vanilla encoder already I have talked about. What are the sparse encoder? Whatever your Google or Meta gives you, give that. Probably when I search, I might get different answer than when you search. Shall I search? Huh? See, vanilla autoencoder meaning is you are using a base neural network for your, say if you are using a base neural network for, you can use any base, depending on the data you can use anything. For example, if you are using a CNN, your vanilla autoencoder will have a set of CNN layers. So what do you get? Yes, what is the sparse autoencoder? I have written, everything is there. What is the first term is about, you are minimizing the reconstruction. What this loss is? You are minimizing the reconstruction loss, isn't it? So the sparse autoencoder minimizes the reconstruction loss plus what loss? Make some of the, not all. You are making some of the activations, you are making some of the weights to go 0, not all the weights to be 0. You are making here some of the activations to go to 0. What is that error? Yes? What is that? How do I penalize the weights? By doing penalizing the weights, some weights go to 0. Regularization always penalizes. Regularizer term is sometimes also called the penalizer. So what does it do? Plus you are penalizing the activation functions. Activations meaning it is activation functions. Just tell me. By penalizing most of the activations to go 0, what does it do? In the layer, instead of weights being 0, you have activations becoming 0. When the activation themselves become 0, for example, if you have a, I am just writing some random network. If I make this activation 0, then whatever the input is coming to this particular node, all become 0. That means what are you doing? You are discarding some features to be remembered. For example, when what is your name you said? Vaishnavi. What I am discarding? I am discarding the cloth she is wearing in my representation. Irrespective of whatever the cloth she wears, I have to recognize her as Vaishnavi. So I am remembering only those features which are essential. Huh? That's where is your the way you define the loss function is the key. If I don't know anything, what I assume is the distribution of these activations to be a Gaussian, and make that in the penalizing. So it remembers if you weights, if you see the distribution of the weights, not the activation functions. Activation function as a parameter. What is the parameter for activation function? The W's or the phi's. What you are doing, you are making a distribution. If I want to represent this looks like some distribution mu rho by rho I. So rho I is some initial distribution I am assuming. Rho is that what I want to learn from this. So like if you want more in terms of this derivation from the mass that we want to learn, there is a separate theory. Initially I thought I'll do that in detail, but I have skipped that. What I am doing is only the abstract and intuitive explanation in arriving the final equation. I am not mathematically deriving it. Yes? Any question? Yes, what are the answers that you got? How do I do this? What is the term looks like? Just tell me. I'll say what do I need to do in variational autoencoder meanwhile. How does this looks like? Yes, this looks like a KL divergence. Should look similar to KL divergence, or in principle you can the starting point as a KL divergence. What is the KL divergence? You start with the Gaussian, but KL divergence actually minimizes the error between two distributions. And you learn the distribution of phi and minimize that error. So you are learning the distribution from the data and minimizing that error. It's a kind of a KL divergence for the activation function. Rho is a sparsity matrix they call. So how many activations I want to make it to 0? If I don't give that, like if I say, then it is very difficult to define that loss. Rho is typically called what is the sparsity coefficient. So your goal is to, without either heuristically give a sparsity coefficient and minimize the loss, and in most of the cases your results will say that, or do the sparsity analysis, have a quick answer. This is the sparsity for this data. This is the sparsity that you need to pick for this data. Exactly the way we have arrived at. How do I decide this? There is no way to decide. The weights given to the lambda g are the kind of a, it's again a WG. How do I decide? There is no quick and immediate answer for that. You have to either people experimentally do. How do you decide a learning rate? Can you say the 0.01 learning rate works for everything? You can't, isn't it? So you are deciding the learning rate experimentally by saying. So you are deciding the learning rate experimentally by seeing few experiments. That's what is the learning rate is fixed heuristically, and few heuristically. So what are the answers? What are the answers that you got? See, penalize this using KL divergence. This gives you another class of autoencoder. They are called the contrastive autoencoders. So majority people name many different types of encoder, but majority there are vanilla autoencoders, sparse autoencoder, and contrastive autoencoder. What is the main difference between sparse and a contrastive autoencoders? Right. Ask your ChatGPT and then generate an answer and tell me that I'll explain. So that answer will be, because you are seeing the answer and you will understand how you need to analyze the given answer given by your ChatGPT or Meta AI. I didn't search. I thought I'll search and then, yeah, I've got an answer. What is the answer that you have got? Anyone, can you read? Any one of you, can you read? Read.
The main difference between a contrastive autoencoder and a sparse autoencoders are sparse autoencoder imposes a sparsity constraint on the hidden layer.
On the
sparse autoencoder imposes a sparsity constraint on the hidden layer. And in the contrastive autoencoder focuses on minimizing the contrastive loss. That distinguishes between positive and negative samples.
Contrastive, what is the meaning of contrastive loss? I reconstruct the input and I give a variant of input. So I maximize the difference between the noisy input I can give to that reconstructed input. Are you getting the difference? input. I also give the noisy input. How noisy input I can give to this? I am maximizing that. So that I always reconstruct this. See, I am introducing one more. What is the maximum or the contrastive loss is reconstruction loss is there. With reconstruction loss, we are giving one more. We are learning the features only from the data points. From where this measurement coming from, we are not yet doing it. That we will do in the variation level. We are, see, I am seeing 10 of you. I am seeing Vaishnavi. I am seeing Vaishnavi 5 times. In different, say the different styles. But when I see the Vaishnavi 6th time, I have to define Vaishnavi as Vaishnavi only. Or I have to classify Vaishnavi as Vaishnavi only. Every time she has some variation. How maximum variation I can accommodate in this class? If it is above that, I call she not. I am not able to classify she is right. I will classify as non-Vaishnavi. That depends on how much variation I have. Are you with me? So that's why you are maximizing the difference between reconstruction loss and the noisy. That you can so this is being done to make the model insensitive to the variations in the data. That's the second part. See, always you are playing around in these two. One is you want to represent the data and get a features out of the data. That is one thing, that's always there. That's what your goal of autoencoder is. Second thing is you want to learn the autoencoder which is insensitive enough to understand variations within the data. It is maximizing the intra-class differences around. Say for example, I want to decide all these models belong to Hampi. All these pictures, whatever I take, Buddha temple, Virupaksha temple, Krishna temple, stone chariot, whatever the pictures that I take, I want to club them, all of them into a category of Hampi. So I have a lot of variations within that category of Hampi class. So I want to maximize that intra-class difference present in the I want to maximize so that my classification becomes better, my accuracy of classification better. If I want to maximize this, then I can apply these such models into the anomaly detection or some other examples where whatever the classes data you are getting is entirely very different than what you have seen. Are you getting this? That's why the contrastive encoder or autoencoders class are used in the exam or the problems like anomaly detection. And autoencoder or sparse autoencoders are used in the and contrastive autoencoders also used in the generative. The concept is used in generative. We talk about that issue. So, what you are saying something? You are reading. I'm just explaining what is reading, how to infer, and how conceptually that you can put into your thing.
The other one is regarding sparse autoencoder, enhancing learning more efficient and compressed representation by identifying key features.
don't know why. I also gave the difference between sparse and contrastive. What is the sparse? And most of all these are also called regularized encoders. Why they are regularized? You always have a regularization term. Regularization term added to your reconstruction class. You are not just doing L of x minus x cap square. You are also adding a regularizer in your cost function. See, the concept of cost and the minimization, your back propagation exactly remain the same. That won't change at all. That's why I'm always trying to connect you with the cost function, regularizer and the back propagation every time when we talk about any of the concept or any of the variants of deep learning models. So what it says, sparse it says, minimize reconstruction error, penalize activations. Contrastive, minimize reconstruction error while maximizing the difference between reconstructed input and the corrupted input. That means what is the maximum noisy input that it can give. That's what is the contrast. Next, see, the regularizer in sparse is different than the regularizer in the contrast. See, the regular sparse you are making activations to go to 0. In the contrastive, what you are doing? What are you making? You are making the features robust to the variations from the input. That's what your regularizer does. Your regularizer includes the contrasting the reconstructed input, the variant of input. That is the key. That is the key. So what are the problems with both of them? Most of the time for both you can use either L1 or L2 regularization or L1 and L2 norm. What is the L1 norm, L2 norm? L1 norm you are taking absolute, L2 norm is a square. You also, last time also I said, also check with the L infinity norm. And people use different norms, but at least understand at least L1 and L2 norm. L1 norm is the absolute norm, the absolute value, the difference between the x and the x dash, and the L2 norm is the square of value. This is it. Error in the case of L1 norm is a absolute error. The error in the L2 norm is a SSD. The sum of square differences. Is the sum of absolute differences is the error in the L1 norm. So what are the challenges or the problems with both of them? What are the problems with both of them? Either autoencoder or any variant of autoencoder. What are the problems? Problems or challenges? Either a vanilla autoencoder or any variants of autoencoder. What are the challenges? What are the challenges? What are the challenges? What are the challenges? Say, for example, I have a data variation like this. If the data comes here, or if the new data comes here. Oh. What is that we need to do? Share Allah. No, here they say.
This one. Let's copy option as well. Actually, I think it's been closed.
Hello,
Either it has been disconnected or something. We have 1 minute here. We can share the screen and then it will come. It's not connecting now.
Disconnected.
Yes.
Network is disconnected.
This one is connected now.
But where the screen went?
This one. You can do that now.
No, where is my previous screen?
Previous one, this one.
So what are the challenges? Challenges with autoencoder. See, I have seen all this data. When the new data comes in here, or when the new data comes in here, when the new data comes in here, does it allow the new data? Because you are doing the inferences from the data that you have seen. Whatever the data we have seen, we are trying to fit a curve or fit some function, so that when the new sample or the new measurement comes in, I can do similar as per the fitted curve. I can do the classification, whatever I want to do on that. How do I model or learn the distribution of the data? Are you getting? One is fit a curve on the data that I have observed. The other one is learn the distribution of the data. What do I mean by learn the distribution of the data? What do I mean learn the distribution? When I take a sample, sample is coming from a sample space, and that sample space can be probabilistically modeled as it is coming from its distribution. It is coming from its distribution. When I know, or when I model from where that data is coming from, my inferences becomes much better. Why? I am not learning only the data, I am learning the distribution from which it is coming from. Are you getting? What I have is, I have a fixed data measurements. I have, maybe the distribution space is very huge, but I have only small measurements done. From the small measurements done, I'm making a small one curve and then trying to know the data. Instead of that, what is been done is learn the distribution of the data. What is meaning of learn the distribution of the data? I have this, fit a model, fit a distribution of this data model. That means I'm making the distribution is coming from the Gaussian and with some mean and variance, some mu and sigma. What I'm learning this. I'm not learning the individual data samples and the curve fit out of that samples. I'm learning this. When I'm learning the distribution, when the new data comes in, what I'm saying is, does it coming from the same distribution or not? If the answer is yes, then I'm making an inference depending on that. What is that you are doing here? In AE, so I have a X, I have a latent space Z, and getting back to X dash. So what I have observed X. I want to give X cap. Observed X, and what I am doing is estimator of X. Whatever I am doing from the given sample, estimate, maximize the likelihood of occurrence of X. So whatever the data I am distributing, maximize the likelihood of occurrence of X, which is called MLE. All autoencoders, whatever we have been done so far, they are doing maximizing the X given Z. What I am doing? I am doing X cap from Z. What is X cap? Is maximizing the probability of it is as close as X. What you are doing is you are actually maximizing this. In other words, what we are saying is maximize or Z given X. You know this distribution which is derived from X, which has X given Z into P of, what is this? Bayes theorem. What is the Bayes theorem for this? P of Z given X. What is the Bayes theorem? Fill in the blanks. Huh? This is called posteriori. Huh? This is likelihood. This is called prior. Always posterior is equal to likelihood by prior. I have given all the meanings. At least now fill in the gaps. P of Z divided by P of x. What we are interested in this. So P of x given z becomes what? P of z given x into P of x divided by P of. How do I know this and how do I compute this? If you learn the distribution of the data, then it is a distribution, probabilistic distribution of the data, and incorporate in the estimation of x cap, then it is called VAE, which is variational autoencoders. So what the variational autoencoder? It provides the method to describe distribution of data in the latent space. That is the key. When I know distribution of the data in the latent space, my inferences become much better. Why? Sampada, show them the outcomes from AE and VAE for a simple MNIST data set. Show in the group you show the outcome from autoencoder and the outcome from AE and VAE. Why? See, when I think I had a nice video, I think it's not available here. When you see, I think they are available if you just search. When you do the how zero sample space is coming from. Variance of 0 coming from 8, coming from 6, coming from 4, from all the given samples of 1 to 9, how all of them get mapped to 0. That's what this term is trying to do. What is P of Z? Is a total probability, isn't it? Which is the sum of all the, I am giving you MNIST data because that's where you connect much faster. P of Z is occurrence of 0 given all, occurrence of 1 given all, occurrence of 2 given all, so on, you sum over all of them. That's what is P of Z, isn't it? P of Z is what? Is the total probability of your sample space. How the distribution of or occurrence of 0, how do you write 0 and how do you write 4? What is the space looks like? For 0, 1, 2, for VAE there is a nice experimentally or visually represented space. So share in the WhatsApp group how that data is being derived. The variational autoencoder is capturing the distribution of the data. So how do I do it? Instead of maximizing its occurrence, what you are doing is instead of just doing this likelihood, you are doing this. You also need this. What you are needing is, how does my latent space, distribution of the latent space looks like given Z? What does this mean? This is posteriori. How does my latent space Z looks like for this data? Only seen data is X. But how does my distribution space looks like? And what is the prior of P of Z gives you what? P of Z, though it is, the first is understanding, next is it easy to compute all the parameters? That's the secondary. It's not always easy to compute P of Z. Always P of Z is hard to compute. It's the prior information of the data, from where it is coming from. We don't know all the variations present. Because we don't know all the variations present, it is harder to compute P of Z. Most of the time, that's why we replace P of Z by a very simple prior, which is Gaussian. What is the prior knowledge I have? Prior knowledge, always what I have is the data to be not very random. When the data is not random, what I assume, it has to obey the Gaussian. What the Gaussian says? It's a continuity. Gaussian distribution says continuity. That is one of the reasons why always we assume it to be Gaussian. Second reason for assuming most of the distribution to be Gaussian is, when we add any different distribution number of times, it eventually obeys Gaussian, the central limit theorem. Why most of the natural phenomena, or if we don't know, we assume it to be Gaussian? Because of central limit theorem. What the central limit theorem says is, if I add any random distributions sufficiently, then the underlying distribution of this addition of all these lead to a Gaussian distribution. In the case of uniform distribution, the value of n is 12. And when you are doing all these your parameters, the way your sampling space, or when you look into the sample space, it is much higher than whatever the n required for the samples, for the central limit theorem. You can very fairly assume that it to be Gaussian. That is a validation for why you are using a Gaussian distribution. Assume that prior to be Gaussian distribution. Then do all the neat math available in variational statistics, which is called variational optimization. There is a very clean methodologies available. That's why people directly from AE move to VAE, which is called a variational autoencoder. Other than the reconstruction loss, you also add as I said, P of Z is P of Z is equal to X is very difficult to achieve. What we assume is, start with Q of Z is equal to X, which is known. Say I assume it to be Gaussian, and have actually P of Z is equal to given to X is actual distribution of the latent space of X, and minimize this error. What are you minimizing? You are minimizing the distribution, two distributions. I think here this minimization, it is a KL divergence between the two distributions. Instead of minus, I'll just use a KL divergence. But what is the KL divergence? What is the KL divergence? I think you have studied that in the PCA as well. PCA you define the basis. Actually PCA or your SVD all talk about the distribution. So what you are doing is you are minimizing the KL divergence. Has a nice mathematical equation where you are minimizing the loss between two distributions, not the outcome from the distributions. Are you getting? Outcomes, what are these measurements? When I click a photograph of this room, and if this photograph is of the size say 1024 by 1024, this is coming from the sample space of images of 1024 by 1024 with each pixel taking RGB value, which is finite set. Yes or no? Is it a finite? It is a finite set because each value takes RGB. Each can take say 256 any of the 256 value, and 1024 by such value, 1024 by 1024. What is that sample space? Looks like it's finite. It's very huge, but it is finite. This is one sample from that sample space. So in the KL divergence, what you are doing is you are minimizing the error between two different distributions. How close are they? If I want to do minimize between two functions, or if I say how close they are, how do you do it? If I give you two functions, when I say how close they are, what do you do? Yes? How do you, what differences do you take? What differences do you take? One is f of x, other one is g of x. What differences do you take? Yes, always when I want to compare, we take a differences. But in what space are you taking a difference? What do you mean by take a difference? I agree, you take a difference between these two. But what is that quantity that you mean I take a difference? Yes? Have you heard about correlation? Correlation between two functions, correlation? Yes? What the correlation defines? How does the correlation define? Have you heard about covariance? Covariance. All of you studied probability theory, na? Yes or no? How do I define the covariance between two random variables? x and y. Huh? It is x minus mean. Is it so? Covariance of x and x comma y. Yes? That's all? Is it so? Covariance of x comma y, is it a matrix or is it a one value? Covariance of x comma y, is it a matrix or is a one value parameter? Yes? Covariance of x comma y, is it a matrix or it's one value? Close that door. Is it a matrix or is it a one value? Hey, remind me, I have a meeting at 3:30. Only 5 minutes, huh? Actually, I thought of completing variational autoencoder today. I think last time, what is the covariance between 2x? It is a matrix or it's a single value? At least tell me that. Covariance of x comma y is a single value? Covariance of x comma y. Single value matrix. Huh? Equal to 0. I still am not talking about if it is 0, what is the meaning? If it is 1, what is the meaning? I am not talking about that. What I am talking is covariance of x comma y. X, y are two random variables. Is it a one value or is it a matrix? X and y, you have two variables. If it is more than 2, matrix. If it is 2, it is single value. Who said? Huh? Read. Huh?
Covariance can be single value or an index. Single value belonging to two random variables. The covariance between them is a single scalar value. This value indicates how much the two variables vary together. Matrix, when working with more than two random variables, the covariance between all pairs of variables can be represented.
ChatGPT ಏನಿದೆ ChatGPT ಅಂತಾರೆ. It's wrong. So, not more than two variables. For two variable itself is a vector. This is for two variable, it's a 2 by 2 vector. This is expectation of x comma x. This is expectation of x comma y. This is expectation of y comma x. And this is expectation of y comma y. This is what is the covariance between x and y. And when the x and y are independent, then these two terms to be equal to 0, then you have a identity matrix where you have only the variances in individual, and usually this covariance, if it is a n dimensional, x1, x2, each of them are random variable. If it is a sigma, which is typically referred as sigma 1 square up to sigma n square, then all of them are x1 to xn are independent. That's the meaning. That's why usually when most of the time we assume all the variables are independent to each other, though they are strictly not independent. For computing ease, always we assume all of them to be independent and analyze or put all these mathematical sane concepts into it and arrive at a solution. If I assume they are to be very not independent, your life becomes much more complex. So now it is I have defined the covariance. What was the question? How do I define similarity between? What is the covariance gives you? I gave the analysis of independence, everything. What is the covariance gives you? If they are not zero, what does this gives you? What is the variance giving you? What is the meaning of variance in a single random variable? You have computed now. Variance have you computed or not? In class 6th, 7th you have computed, isn't it? Class A performance is this, class B performance this. What is the mean of the class? What is the variance of the class? If the variance is more, that class is not good. Such problems you have done it or not? You have done, isn't it? What is the variance giving you?
Relation between how they increase or decrease when parameters are increased. For example,
How deviated are from the mean? How each of the sample is deviated from the, what's the mean is variance is giving you? How far all the samples are deviated from the mean? Eventually you want the same behavior meaning or good from that perspective, you want all to be around the mean. You don't want to be variance to be too large. If the variance is too large, then you don't have a much inference which can be derived from that distribution. Can you?
Any significance of sign there and positive?
Positive variance, negative variance. It is just as far as the variance is giving you the physical, not physical, the interpretation of a variance, it doesn't. When you are interpreting mathematically both positive and negative deviations, when you put in the computational deviation or the formal definition of variance, there is no difference. What you want to do is, the mean is a representative of the class or mean is a representative of that distribution. You don't want any deviations not too away from the mean. That's the meaning of a distribution when you talk. Where your positive variances also equally mean the same and the negative mean the maximum scorer of S also mean the same and the fail person also mean the same. It doesn't associate for the distribution, it doesn't associate anything. The meaning of away from the mean remains the same. It doesn't, the positive class affects this way, negative class or the negative mean, negative variance. The variance, there is no positive and negative. Sigma is always positive. The way you compute sigma is always positive. It doesn't. Conceptually, it doesn't. That's why we don't do any analysis for this separately and that separately. In all the statistical inferences, they exactly remain the same. But if you are applying that to a positive class from the distribution and trying to understand in the reinforcement or the federated learning framework, then we need to think. I don't know the answer, quick answer for that. We have to think what is actually we are capturing. Are we capturing in terms of modeling the entire distribution into this distribution framework, or are we doing separate? We have to check. Yes? I think already it's time up. Please go through the basics of variances. Variance, simple variance with one random variable. Covariance when you are taking two random variable. Please check with your Google where you have a good sane answers. At least Wikipedia, by and large the answers are right. I am not 100% saying that also. I am saying by and large the answers are right. Check before arriving your conclusion. So covariance is not scalar when you have two random variables. So I think I'll again start